A deep learning neural network learns to map a set of inputs to a set of outputs from training data. We cannot calculate the perfect weights and biases for a neural network. There are too many unknowns. Instead, the problem of learning is cast as a search of optimization problem, and an algorithm is used to navigate the space of possible set of weights the model may use in order to make good or good enough predictions. Typically, a neural network model is trained using the stochastic gradient descent optimization algorithm, and weights are updated using the backpropagation of error algorithm. The gradient descent algorithm seeks to change the weights so that the next evaluation reduces the error, meaning the optimization algorithm is navigating down the gradient of error. In the context of an optimization algorithm, the function used to evaluate a model is referred to as the objective function. Typically, with neural networks, we seek to minimize the error. As such, the objective function is often referred to as a cost function or a loss function, and the value calculated by the loss function is referred to as simply loss. The loss function has an important job in that it must faithfully distill all aspects of the model down into a single number in such a way that improvement in that number are a sign of a better model. When calculating the error of the model during the optimization process, a loss function must be chosen. This can be a challenging problem, as the function must capture the properties of the problem and be motivated by concerns that are important to the project and stakeholders. Now that we are familiar with the loss function and loss, we need to know what functions to be used. For different problems, we will have different loss functions. A regression predictive modeling problem involves predicting a real value quantity. In this part, we will talk about loss functions that are appropriate for regression predictive modeling problems. We will take a look evaluating 3 common loss functions that are appropriate for a regression predictive modeling problem, which are mean square error loss, mean square logarithmic error loss, and mean absolute error loss. Mean square error is the default loss to be used for regression problem. Mean square error is calculated as the average of the square differences between the predicted and actual values. The result is always positive regardless of the sign of the predicted and actual values, and the perfect value is 0. The squaring means that larger mistakes result in more error than smaller mistakes, meaning that this model is punished for making large mistakes. However, there may be regression problem in which the target value has a spread of values, and when predicting a large value, you may not want to punish a model as heavily as mean square error. Instead, we can first calculate the natural logarithm of each of the predicted values, then calculate the mean square error, and this is called the mean square logarithmic error loss. For some regression problems, the distribution of the target variable may be mostly Gaussian, but may have outliers. For example, large or small values far from the mean value. The mean absolute error loss is an appropriate loss function in this case, as it is most robust to outliers. It is calculated as the average of the absolute difference between the actual and predicted values. Now we'll take a look at different loss functions for classification problems. Binary classification are those predictive modeling problems where examples are assigned 1 out of 2 labels. The problem is often framed as predicting a value of 0 or 1 for the first or second class, and is often implemented as predicting the probabilities of the example belonging to class value 1. Cross-entropy is the default loss function to be used for binary classification problems. Mathematically, it is the preferred loss function under the inference framework of maximum likelihood. Cross-entropy will calculate the score that summarizes the average difference between the actual and predicted probability distribution for predicting class 1. The score should be minimized, and a perfect cross-entropy value is 0. An alternative to cross-entropy for binary classification problem is called hinge loss function, primarily developed for use with support vector machine models. The hinge loss function encourages example to have the correct sign, assigning more error when there is a difference in the sign between the actual and predicted class values. In terms of multi-class classification problem, these are predictive modeling problems where examples are assigned 1 out of more than 2 classes. Multi-class cross-entropy is the default loss function to be used for multi-class classification problems. Multi-class cross-entropy will calculate a score that summarizes the average difference between the actual and predicted probability distribution for all classes in the problem. The score should be minimized, and a perfect cross-entropy value is also 0. A possible cause of frustration when using cross-entropy with classification problems with a large number of labels is the one-hot encoding process. For instance, predicting words in a vocabulary may have tens or hundreds of thousands of categories, one for each label. This can mean that the target element of each training example may require a one-hot encoded vector with tens or hundreds of thousands of 0 values, requiring significant memories. Sparse cross-entropy addresses this by performing the same cross-entropy calculation of error without requiring that the target variable to be one-hot encoded prior to training. Now, after introducing different loss functions in the neural network, let's talk about how we can train a neural network effectively. Gradient descent is an optimization algorithm that is used when training a deep learning model. It is based on the convex function and tweaks its parameters iteratively to minimize a given function to its global minimum. To understand this concept fully, it's important to know about gradients. So, what is exactly gradient? A gradient simply measures the change in all weights with regard to the change in error. You can also think of a gradient as the slope of a function. The higher the gradient, the steeper the slope, and the faster a model can learn. But if the slope is 0, the model stops learning. In mathematical terms, a gradient is a partial derivative with respect to its input. If we try to plot the cost function versus model parameters, we will have a curve. And our objective is to adjust the weights so that we can reach the minimum point of the curve. How big the steps are gradient descent takes into the direction of the local minimum are determined by the learning rates, which figures out how fast or slow we will move towards the optimal weights. For gradient descent to reach the local minimum, we must set the learning rate to an appropriate value, which is neither too low nor too high. This is important because if the steps it takes are too big, it will not reach the local minimum because it bounces back and forth between the convex function of gradient descent. But if you set the learning rate to a very small value, you can still eventually reach the local minimum, but that may take a long time. A good way to make sure gradient descent runs properly is by plotting the cost function as the optimization runs. Put the number of iterations on the x-axis and the value of the cost function on the y-axis. This helps you see the value of your cost function after each iteration of gradient descent and provides a way to easily spot how appropriate your training rate is. You can just try different values for it and plot them all together. The left image shows such a plot, while the image on the right illustrates the difference between good and bad learning rates. If gradient descent is working properly, the cost function should decrease after each iteration. When gradient descent cannot decrease the cost function anymore and remains more or less on the same level, it has converged. The number of iterations a gradient descent needs to converge can sometimes vary a lot. It can take 50 iterations, 60,000, or maybe even millions, making the number of iterations to convergence hard to estimate in advance. Another advantage of monitoring gradient descent via plots is it allows us to easily spot if it doesn't work properly. For example, if the cost function is increasing, most of the time, the reason for an increasing cost function when using gradient descent is a learning rate that's too high. Feed-forward neural networks are inspired by the information processing of one or more neural cells, called neuron. The neuron accepts input signal via its dendrites, which passes the electrical signal down to the cell body. The axon carries the signal out to synapses, which are the connection of a cell's axon to other cells' dendrites. Forward propagation refers to the calculation and storage of intermediate variables for a neural network in order from the input layer to the output layer. The principle of the backpropagation approach is to model a given function by modifying internal weights of input signals to produce an expected output signal. The system is trained using a supervised learning method, where the error between the system's output and the known expected output is presented to the system and used to modify its internal states. Technically, the backpropagation algorithm is a method for calculating the gradient of a neural network parameters and training the weights in a multi-layer feed-forward neural network. In short, the method traverses the network in reverse order, from the output to the input layer, according to the chain rule from calculus. The algorithm stores any intermediate variables called partial derivative, and they require while calculating the gradient with respect to some parameters. Finally, we will talk about some common challenges of neural network training. First is vanishing gradient. Like the sigmoid function, certain activation functions squash an ample input space into a small output space between 0 to 1. Therefore, a large change in the input of the sigmoid function will cause a small change in the output. Hence, the derivative becomes very small. For shallow networks with only a few layers that use these activations, this isn't a big problem. However, when more layers are added up, it can cause the gradient to be too small for training to work effectively. Another potential problem is called exploding gradients. Exploding gradients are problems where significant error gradients accumulate and result in a very large update to neural network model weights during training. An unstable network can result when there are exploding gradients, and the learning cannot be completed. The values of the weights can also become so large as to overflow and result in something called NaN values. One simple solution to solve vanishing gradient and exploding gradient is to use other activation functions, such as redu, which doesn't cause a small derivative or large derivative. Another way is to use batch normalization, which can simply normalize the input x so that the derivative won't be too small. And here comes the end of the first part, artificial neural network and fully connected neural networks. In this section, we talk about the overview of the artificial neural network and fully connected architecture structure. And we also talk about multiple components in such a neural network, for example, activation functions, loss function, and gradient descent, which is the algorithm to train a neural network effectively. We hope you enjoyed the session, and we will talk about convolutional neural networks in the next section.